A tiny event in Brazil, like a butterfly flapping its wings, could lead to a major weather event far away, like a hurricane in Indonesia. Edward Norton Lawrence, 1893, Kyoto, Japan. Young lawyer Henry Stimson and his wife, Mabel White, are on their honeymoon in Kyoto. The newlyweds are captivated by the vibrant Oriental city and its rich history, a visit they will cherish for the rest of their lives. May 11, 1945, Los Alamos, USA. A special U.S. Army committee prioritizes targets for atomic bombings, placing Kyoto at the top as Japan's largest industrial center. However, citing its significant cultural heritage, Secretary of War Henry Stimson personally removed Kyoto from the list, making Hiroshima the primary target for the U.S. Army. Next in line for bombing is the town of Kokura, August 9, 1945, Japan. The crew of the U.S. Air Force B-29 bomber receives an important order to destroy the military arsenal in Kokura with a powerful new bomb. However, thick fog obscures the target, leading aircraft Captain Charles Sweeney to redirect the mission to Nagasaki. Thus, a sentimental memory from 50 years earlier and an ordinary weather event influenced the destinies of millions. This story exemplifies how seemingly small events can lead to significant consequences, a phenomenon known as the butterfly effect. This is actually part of the larger field of science called chaos theory. An unexpected discovery of chaos. A butterfly takes flight. To understand the surprising link between tiny changes and massive weather events, let's revisit a groundbreaking discovery in 1961. Edward Lorenz, a mathematician and meteorologist, aimed to use powerful computers to predict weather patterns with unmatched accuracy. However, his calculations yielded unexpected results. To speed things up, Lorenz divided the calculations into steps, using the previous step's results as the starting point for the next. The computer rounded some intermediate values, a seemingly insignificant detail. Much to Lorenz's surprise, the continuous and step-by-step calculations produced vastly different outcomes. Further investigation revealed that the equations used weren't perfect for modeling atmospheric processes. Yet as science often goes, this unexpected hurdle led to a remarkable discovery. Lorenz's work, though initially flawed in its approach, paved the way for the theory of chaos, demonstrating how tiny changes can have dramatic and unpredictable consequences. The butterfly effect. A tiny change, a big impact. Edward Lorenz, a mathematician, was studying weather patterns with the help of computers. He expected the powerful machines to provide highly accurate forecasts. However, his calculations surprised him. To speed things up, Lorenz broke down the calculations into steps. Tiny rounding errors were introduced during these steps, something he considered insignificant. But here's the twist. These seemingly minor changes dramatically altered the final results. Further investigation revealed why. The equations used weren't perfect for capturing the complexities of weather. While the initial approach had limitations, it led Lorenz to a crucial discovery. The tiny errors behaved like a butterfly flapping its wings. Even the slightest change in starting conditions could cause the system to veer dramatically in a different direction, ultimately producing vastly different outcomes. This became known as the butterfly effect. Chaos theory, unveiling order in the unpredictable. Chaos theory, a concept that has evolved with contributions from numerous scientists, explores seemingly random behavior in systems governed by underlying laws. It applies to a vast array of phenomena, from turbulent weather patterns to the evolution of life and even the stock market. While chaotic systems appear erratic, they are not truly random. They operate under complex, deterministic laws that make long-term predictions difficult. This is what sets them apart from truly random systems, where events are unpredictable by nature, like the decay of radioactive material. In chaotic systems, even tiny variations in starting conditions can lead to drastically different outcomes, making them highly sensitive and fascinating. Chaos theory, decoding the messy. Chaos theory might seem like an intimidating concept for non-mathematicians, but fear not. Here's a breakdown in simpler terms. Imagine a system that responds to your influence in unexpected ways. Push it a little, and the outcome might be much bigger or smaller than expected. That's a key feature of chaos, non-linearity. Now, imagine starting a process twice with nearly identical conditions. In chaos theory, these tiny differences can snowball, leading the system down completely different paths. This is the essence of the butterfly effect. Finally, chaotic systems involve intricate interactions between their parts. Unlike classical physics, this can't be ignored. It's like a complex dance where every move influences the others. Capturing these intricate relationships makes chaos theory models powerful and realistic. Think about the early universe, a swirling storm of particles. Chaos theory helps us understand how such seemingly random events might be governed by underlying laws, even if their exact outcomes are unpredictable. A journey back to the beginning of times. Imagine a time before time itself, mere moments after the Big Bang. No familiar matter or energy exists, and the fundamental forces are unified in a strange dance. Our known physics doesn't apply here, but different. Equally strict laws govern this nascent universe. Crucially, even the tiniest fluctuation at this point could completely alter its destiny. In a very real sense, our reality was born from chaos. Fast forward a million years, the vast emptiness is now filled with swirling clouds of primordial hydrogen clumping together under the pull of gravity. These are the seeds of the first stars, scattered unevenly across the cosmos. Each is massive enough to influence its neighbors, and any nudge, any slight difference in mass could send the revolution down a completely different path. Chaos still reigns supreme. Over billions of years, these first stars burn bright and die spectacularly, forging the heavier elements that would later become the building blocks of planets. New generations of stars ignite, surrounded by swirling disks of cosmic dust. The chaotic dance continues, shaping the destiny of these newborn stellar nurseries. And from one such dance, 4.5 billion years ago, our own solar system emerged. Even in its formation, the echoes of chaos resonate, a testament to the unpredictable yet fascinating birth of our universe. The story of chaos could unfold endlessly, from the explosive birth and death of stars to the swirling dance of weather patterns in our atmosphere. The fingerprints of deterministic chaos are everywhere. Its intricate laws influence the paths of our lives, shaping economies and societies. The universe is a vast tapestry woven from countless interconnected threads, and we are all part of this grand design. And who knows, perhaps a seemingly insignificant event, like a butterfly's flutter on a distant continent, is already setting the stage for a future we can't even imagine. And if you like this video, click the next one shown on the screen. I'm sure you'll like it. Thanks for watching.